My talk today is about the power of quantum technology. As a warning, there are some pretty wacky concepts for those who are not familiar with quantum physics or quantum computing. And as I was preparing for this, I was a little nervous about talking about some of these concepts, but I also couldn't help but be in awe that this is really an unveiling of God's creation. And so I just pray that in my talk, in this presentation, that I can really reflect that well. And I ask that we all have that as an open mind as we kind of explore some of these concepts. So just a bit about myself. As the intro suggests, I was compelled by this a personal and professional mission and calling to really work at companies and work on products that democratize access to information and opportunity. And it's led me to a variety of companies and a variety of efforts, from startups to founding my own company to a few big tech companies. And now currently at a company called Q Control, where we are pioneering a lot of quantum software that tries to stabilize quantum hardware, quantum computers. Um, and so, as I was considering a vocation, especially during the pandemic, I couldn't help but think of anything that was more transformative than quantum technology. And I'm hoping that all of us can really kind of see that this is just an exciting area of science that, God has really endowed us to really explore. When most people hear of the word quantum, you may think of Ant-Man, Quantumania. You may think of Doctor Strange as he was coming up with the tens of thousands and millions of possibilities and having that one path to success. So they're all drawing from elements of quantum technology. And for those who are really into Black Mirror, you may be familiar with one episode that was talking about the mix and a combination, a cautionary tale of quantum technology and AI mixed together. And even Oppenheimer, drawing from elements what I really appreciated was some of the conversations that he had with some of the early scientists and pioneers of quantum physics as well. But even more recently in culture, you may be aware of this year's Nobel Prize in Physics, which was awarded to three pioneers whose experiments in the 1980s laid the foundation for what we see as quantum computing today. So it's really feels like there's kind of this moment right now where quantum computing, quantum technology is really bubbling up. Just a little quick aside about my company, and I won't dwell too much on this, but my company, Q Control, it's focused on making quantum technology useful. Since we were founded, the company has been building and delivering enterprise grade dual use software solutions. So what that means is we take a lot of our science expertise in quantum control and we build that, turn it into infrastructure software that on one hand, on the left side, we maximize the performance of quantum computers. But then we also deploy that, if you look on the right side, deploy that as software solutions for quantum sensors, especially for navigation. And most recently, it was awarded as one of the best inventions by Time Magazine. So this is a sensor where we deploy our software, and you can imagine a sensor that can help vehicles navigate even when GPS is not available. On the quantum computing side, which is really kind of the focus of this talk, is the problem today is that quantum computers are noisy and error prone. So we build AI powered and error reducing software so that we can unlock the actual performance that these computers are supposed to deliver. Otherwise, people who experience and interact with computers today are will just get random noise, random output, and it kind of defeats the purpose of actually using a quantum computer. And to illustrate this, take, for example, an image that you see here. Just an illustration of what the image is supposed to look like. This is an ideal representation that you can kind of get from either classical solutions or even a simulator. And then a bare metal quantum computer today, without any kind of software, will typically produce something like this. So you can tell that it doesn't represent that image at all. But with our software, we suppress that noise, reduce any errors wherever they occur in the computer, so that you actually get the closest match to what the ideal is like. And so as I talk more about quantum computing, I just wanted to give it a quick aside about computation as a whole. So humans have been building computers for thousands of years. Every time we understand a new field of physics, we design a new computer that harnesses this newfound knowledge. And once we understood geometry and mechanics, we built simple computers like the abacus. And once we invented mechanical gears, we built more complicated adding and subtracting machines. So analog versions of today's computers. We built more complex machines like astronomical clocks, which could predict the positions of planets and stars and calculate movable holidays that depended on the cycle of the moon. And many can still be found in operation today. Even the slide rule is a simple analog computer that was still commonly in use until the late 20th century. All of these devices are computers, machines that simply take input information, process it in some predetermined way, and then get some output, which is hopefully the answer, to the question that was submitted. And these are all analog computers built to solve a specific problem. And then we mastered electricity, transistor circuits. We use this knowledge to build today's electrical digital computers, which are reprogrammable and can solve many types of problems. And we call these classical computers, which I'll refer to throughout my talk. And of course, that's the computer in which I'm presenting from right now, because they're entirely described by classical physics, the sort of physics that we encounter every day. And so now, as our mastery and understanding of quantum physics grows, which I honestly believe is an area that God is unveiling and revealing more and more and equipping more and more pioneers and scientists to discover. We're doing it again today. We're harnessing that knowledge, this new area of physics, to build a new form of computer. Um, and this type of computer is one in which can solve new types of problems. So I'll ask that you bear with me a little bit at explaining a core concept of quantum physics called superposition. So this is an attempt at describing it. So quantum physics has this reputation of being unapproachable or even magical. In reality, it's just unintuitive. So if you take, for example, the theory of gravity, it feels much more approachable than quantum physics because we can go outside, throw a ball, and see it works, see it fall down. But we can't split an atom in our kitchen. We can't witness superposition, which I'll try to describe here. We can't witness it with our bare eyes. And this is because what if you want to see quantum effects, you have to, if you want an object to act quantumy, then it must be very, very small, very, very cold, and very isolated. So anytime something tries to interact with that object, it becomes a little less quantum and a more classical. So to just illustrate this, let's take, for example, flipping a coin. In the classical world, objects are in fixed locations. A coin is either heads or tails. So even when you flip it, the odds of getting heads or tails is 50%. Once it lands, then it definitely is in one state. But in quantum physics, even after the coin toss, the coin exists simultaneously as heads or tails. And so in mathematical terms, we call it probability distribution, which has some chance of finding the coin in heads and some chance of finding it in tails. And so in quantum computing, we think about superposition occurring at different energy levels. And so, you know, the way I like to think of this area of physics is really in some ways reflecting the way God designed creation to both have certainty as well as possibility. So just bookmark this because it's a core concept of physics. But a great resource, in all seriousness, is Quantum Computing for Babies. It's a book I read before I joined the company, and it's a book that I know many people read, even with PhDs in the field. So a regular computer, the information is stored in a bit. So that's kind of represented by this ball here. And these are tiny switches that could be either 0 or 1. But a quantum computer, the information lives in a qubit. So it's a quantum bit, which can be 0 or 1. Um, Basically, both a probability of 0 and 1. And again, that is superposition as illustrated in that coin analogy before. So what does this mean? This simple difference unlocks an entirely new way of processing information and running calculations. So, and bear with me with this illustration, a classical byte is 8 bits, and that can represent 2 to the eighth or 256 combinations. A quantum computer, one quantum 8 qubit equivalent, it can also represent 256 combinations. But the key difference is that to check the total possible number of combinations, a classical computer would have to perform all of these operations sequentially. So that's why sometimes it takes a bit of time to run really, really complex operations. But a quantum computer can check all 256 combinations at the same time in a single operation. 1,024 states. 30 qubits can be almost a billion states. And if you go to 300 qubits, a 300 qubit computer, it can process more states than the number of atoms in the observable universe. So that's how you can start to see why these computers can be quite powerful. But the exciting thing is that we see companies more and more, even recently, even as of yesterday, all these companies from IBM, IonQ, Quantinuum, all coming out with new roadmaps and actually delivering on them. So we know that these these devices are iterating and evolving. So it is almost a matter of time that we will have these large computers. And then that allows us to be in the near future, these large computers will be much more capable, arriving at solutions to intractable problems much faster than classical computers, and or solve new problems that today's computers wouldn't even be able to solve. That is what we call quantum advantage. Sometimes people describe that as the chat GPT moment, but I think it's going to be a bit more gradual. But again, noise prevents us from really reaching this today. And again, this is still an area of science that's constantly evolving, but the hopeful thing is that this trend is upwards. So what kinds of problems, real world problems, can these devices actually be used for? So I'll give a few examples. And again, I want you to kind of bookmark these because I think there are implications and things that we can imagine this being used for missions. So if you take a classical logistics problem, imagine you have to deliver 4 packages to 4 different locations. They need to go to a depot to be sent and returned, and you're trying to identify what the best round trip is. And so let's say we only care about the fastest delivery routes. This is on the left-hand side, this is an example of two possibilities. It's pretty easy to do even in our heads, and very easy to do with a classical computer. But in reality, things are more complicated. There are more variables, time, fuel, emissions, and not to mention, as the number of depots, the number of vehicles, delivery sites, and packages increases, this problem becomes very, very hard, and very soon involves countless possible combinations in variables, and becomes too many options with too many considerations. And so today's computers, classical computers, they struggle with the number of these possibilities as they grow exponentially. But quantum computers can evaluate these options um, almost instantly, depending on the number of variables, almost in one operation, as kind of described before. And one of the exciting things is that even with our company, we're starting to analyze these real world use cases. We looked at London Bridge and the number of trains that were coming and going, and trying to optimize the arrival times. And I imagine many of you all may have actually been at this transit site over, as you're visiting. And we were able to discover that today, on today's computers, we can actually solve a problem that's 6 times larger than what was previously solved. And that's again because of the growth and the increase in these devices. And we're able to do so. What's also exciting is that you can do it at a significantly lower compute cost, which is also a huge consideration in which we think about advantage. So we're starting to see um, signs that there is um, advantage as well as just commercial ROI that's starting to come. And then what an area that I'm really excited about is that these kinds of computers can really accelerate um, things like drug discovery and discovery of new medicines, new cures. Um, this area of science can simulate atoms and molecules. Um, and it's not even just for research. Simulating these molecules would lead to faster drug development, new materials for clean energy production and transmission in food technology. And so, uh, I'll skip this. I wanted to mention just that there's a lot of conversation, especially from the previous speaker from Perplexity. There's a lot of synergy and symbiotic relationship between quantum and AI as well, which is really exciting. We use AI today for a lot of our development, but in the future, once these computers are large enough, you can use AI to also accelerate, model training, improve some of the models as well. So that will all be coming soon. Now, I want to focus on this part, which is what does this mean for what can we imagine this meaning for the church and global missions? Um, you know, just some of the examples I've been thinking about, especially with some of the work I do with mission organizations, is, take, for example, drug discovery, healing as a witness of God's love, quantum-driven breakthroughs in medicine and accelerations in drug discovery can really help provide low-cost medicine and develop much faster. So this is an area that I definitely think a lot about in terms of and what motivates me to even work in this field. And then earlier today, the speaker from Biblica as well, talking about how do we make the gospel more accessible. Think about the logistics examples, better access and more encrypted delivery of the message in more secure locations. So this allows us to support these kinds of resources, discipleship resources, especially where infrastructure is very fragile. And then last but not least, again, these are just a few different examples, but reaching the unreached, especially where access is hard or it's dangerous. And so if you think about the quantum secure communication can really provide a really robust way of delivering digital ministry messages and digital resources as well. And so this is also an area where quantum technology can actually provide more secure and safe communication. Um, Obviously, there are risks involved, which I'll save that for another talk. But these are things that we can use for our advantage. I'll end off with this, which is, last week I was at a conference and there was a guest artist who was a child prodigy, and I really wanted to reflect on Ephesians 6:12, which says, "For our struggle is not against flesh and blood, but against the rulers, against the authorities, against the powers of this dark world, and against the spiritual forces of evil in the heavenly realm." Quantum physics has this is typically called the science of the unseen, because it's not intuitive. And what's really exciting is that even scientists I work with, who are typically, not spiritual, they don't believe in God, they even admit that there is this unseen realm. There's this undescribable force. And I came across this quote from this artist, if it shows up. Yeah, is that she had this quote that said, with this art piece, is that my hope is for my art to be a small bridge between heaven and earth, between the invisible and the visible. And I just found that so exciting um, because I thought that just really reflected um, what this area of science is, why it's exciting, and why I wanted to share it today with you. So let me know if you have any questions, and I hope to connect with many of you in the future. Thank you.